All right, section 6.2, integration by substitution. You're going to love today's problems. They're going to be more complex integration problems. So life is going to get a little more complicated as we work through these problems. So let's go ahead and dig in and see what happens and see what's different. So we have the integration, example 1, of x times the quantity of x plus 3 to the third dx. To integrate this, well, we're going to say, hey, u is going to be that part in the quantity, the x plus 3. Well, in that case, our du then is going to be, well, the derivative of x is 1, derivative of 3 is 0, so we end up with a 1 dx. Coming back to my integration, well, I have an x dx. I only have a 1 dx out here. So this x has to stay with our integrand at this point. So we have x times the integration of u to the fourth du, since dx equals du. But remember, at the beginning, when we started u substitution, I told you that the variables in the integrand has to be the same as the variable of integration. That's our problem. We have to get this x in terms of u. Well, what are we going to do with that, and how are we going to find it? If we come back up to the substitution, we know that u equaled x plus 3. So solving this for x, we can subtract that 3 over and get u minus 3 equals x. So now we have the integration of u minus 3, the quantity, times u to the fourth du. Some of you might be saying, well, that looks kind of ugly. And it does. What we can do is we can take that u to the fourth and bring it in to the quantity and end up with the integration of u to the fifth minus 3u to the fourth du. Now we can integrate each part of this integrand. The integration of u to the fifth is u to the sixth over 6. The integration of 3u to the fourth is 3u to the fifth over 5 plus c. We can replace our u with x plus 3. So we get the quantity of x plus 3 to the sixth over 6 minus 3 times the quantity of x plus 3 to the fifth over 5 plus c. Again, I'm going to ask for a common denominator. So our common denominator is going to be 30. So we're going to end up with 5 times the quantity of x plus 6 to the sixth minus 18 times the quantity of x plus 3 to the fifth plus c. Again, remember, we're going to leave that plus c out there to the side. We're going to leave it. It's a variable that is very fluid, so we want to just leave it and not put it in with a common denominator. Well, if I look at this numerator, I can clean that up. So I can factor an x plus 6 to the fifth out, and we're going to be left with a 5 times x plus 6. Since we had 6 of them here, taking 5 out, we're left with 1 minus 18 all over 30. Again, plus c is on the outside there. Cleaning up inside those brackets, we have x plus 6 to the fifth. We multiply this 5 through, so we get 5x plus 30, then minus our 18. So we have 5x plus 12. 30 minus 18 gives us our 12. That's over 30 plus c. And there, my friends, is our original function f of x. Notice how nice and juicy this problem is. And notice this is only example number 1. So example 2. We're going to integrate x to the third times the quantity of x squared plus 1 to the fourth dx. Again, I'm going to do my u. My u is, again, normally the quantity, the inside of the quantity. So u is going to equal x squared plus 1. du, in this case, is going to be 2x dx. Well, if I look, I have x to the third dx. Don't have the 2. What do we know about x to the third? Well, x to the third we can break up into x squared times x. Since we can add those exponents when we multiply to get back to our third. So now I have an x dx in my integrand that I can pull out when I work with my u's and my du's. So I'm going to get rid of this 2. So 1/2 du equals an x dx. So now my integration becomes 1/2. I still have that x squared times u to the 4th, and my x dx is going out, and it's becoming my du and my 1/2 coming in. Again, we got to get rid of these x's. Well, what do we know about x squared? Well, if I come up here, x squared is going to equal u minus 1. So we have the integration. This 1/2, again, remember, is a constant being multiplied. So I can bring it to the outside, kind of leave it for now. So we have 1/2 x squared, which is u minus 1, times u to the 4th du. Now it becomes very similar to what we just did in the previous example. So we have the integration, multiply your u to the 4th through. We have u to the 5th minus u to the 4th du. Again, I'm leaving this 1/2 on the outside. So we have 1/2. The integration of u to the 5th is u to the 6th over 6, minus integration of u to the 4th is u to the 5th over 5. And then we're going to have our plus c. Again, this plus c, very fluid, since it's being added there. If I multiply this 1/2 through, that c is really just going to stay a 1/2 c or c. So I'm going to go ahead and replace my u's with my x squared plus 1. So I get x squared plus 1 to the 6th over 6 minus x squared plus 1 to the 5th over 5 plus our c. I can find a common denominator. So we get 1/2. We have 5 this time. X squared plus 1 to the 6th minus 6 x squared plus 1 to the 5th. That again is over 30 plus c. I'm going to go ahead and factor out my x squared plus 1 to the 5th. So x squared plus 1 to the 5th, my common factor. What are we going to be left with? We're going to be left with 5 times an x squared plus 1 minus 6. And that's all over 30 plus our c. I can go ahead and multiply this 1/2 through, so I get 1/60th. If I multiply that 1/2 to c, I still get plus c, because 1/2 times c is a constant. 1/2 of a constant is still a constant. So we get 1/60th of x squared plus 1 to the 5th times 5x squared. I'll multiply this 5 through, so I get the 5x squared plus 5. 5 minus 6 gives me minus 1. And that gives us our original function, f of x, in nice clean form. I have just a couple more examples. They get a little more complicated as we go through, but not too miserably much more as what we've seen before. Here we have a fraction, x over x plus 2. So normally we'll let that u be the denominator. We're going to do that same thing in this case. We're going to let u equal x plus 2. This gives us our du as being a simple dx. So if I look at my integration substitution, I have x over u du. Again, we got to get that x out of my integrand. So I come up to the top here, and I know that u minus 2 equals x. Well, if u minus 2 equals x, I can do that substitution as u minus 2 over u du. I can break this now up. So remember, we cannot integrate with variables in the numerator and denominator. They'll all have to be in the numerator. So I can break this up into u over u minus 2 over u du. That simplifies to 1 minus 2 over u du. Now I can integrate. Integration of 1 is u. Integration of 2 over u is 2 natural logs of the absolute value of u plus c. We replace the u with x plus 2. So I have x plus 2 minus 2 natural logs of the absolute value of x plus 2 plus c. And some of you might see this as our answer, and that's fine. We can leave it like this. But multiple choice answer, or in the back of the book answer, if we look at this plus 2, what do we know about 2? 2 is, you got it, a constant. Well, if I take 2, which is a constant, plus another constant, well, what is a constant plus a constant? It's going to give us another constant. So that plus 2, or that 2 plus c, is really going to give us another c value. And it's not going to matter if we leave it as the plus 2 or the plus c, but know that we can see it in both forms. And that gives us our nice, clean, original function, f of x. All right. Shall we get a little more ugly? I'll say that for example 5. This one, again, not too miserable. We're going to let u equal x minus 3, du equals dx. I'm coming back to my integration. I have an x squared times u to the 8th du. We got an x squared now. We need a form of x squared. I don't have it. I know that x equals u plus 3. Well, if x equals u plus 3, I can square both sides to get an x squared. So I know that u plus 3 quantity squared equals an x squared. So my integration becomes u plus 3 squared times u to the 8th du. That's ugly, because all we can do at this point is go ahead and multiply out this u plus 3 squared. Well, u plus 3 squared is u squared plus 6u plus 9. And that's going to be multiplied by u to the 8th du. I can now multiply my u to the 8th in. So we get u, remember we multiply, we add the exponents, so we get u to the 10th plus 6u to the 9th plus 9u to the 8th du. We're going to go ahead and integrate, adding 1 to the exponent, so we get u to the 11th over 11, plus 6u to the 10th over 10, plus 9u to the 9th over 9, plus c. Before we find common denominators and replug these u's in, I'm going to go ahead and clean up these u's and these expressions. So we can reduce those 9 over 9s. That's nice. Gets rid of one of our denominators. 6 over u, we can reduce that. 2 goes into both of them. So we have 3 over 5. So now our problem becomes u to the 11th over 11 plus 3u to the 10th over 5 plus u to the 9th plus c. Finding common denominator, now my common denominator is just 55. So I have 55, I have 5 times my u, and I'm going to go ahead and replace my u with x minus 3. So I have 5 x minus 3's to the 11th plus 33 x minus 3's to the 10th plus 55 x minus 3's to the 9th. And this is all over 55 plus c. Looks kind of ugly, but we can work through it here, I think. Again, we can pull out an x minus 3. We have 9 of them in common. Remember, we take out the smallest exponent. So we're left with 5 times x minus 3 squared plus 33 times x minus 3 plus a 55. That's in a bracket there. And that's all over 55. We can clean up this inside the brackets. X minus 3 squared, well, that's x squared minus 6x plus 9. I can multiply my 5 through. So I have x minus 3 to the 9th times 5x squared minus 30x plus 45 plus 33x minus 99, multiply my 33 through, plus 55, that's plus our c all over 55. We're almost there, kids. Multiply the x, or take the x minus 3 to the 9th, still out there, clean up. We have 5x squareds. We have a negative 30x and a positive 33x, so it's going to be a positive 3x. 45, negative 99, and 55. I know 45 and 55, that gives me 100. So 100 minus 99 gives me plus 1. That's over our 55 plus our C, and voila, we got it. One last problem. I saved the doozy for the last one. So we have 1 minus the square root of x over 1 plus the square root of x. As you're looking at this, you might see this as one of your problems in your assignment. Hint, hint, hint. And the other one in your assignment is very close to this, so you should be able to mirror them, hopefully. Hint, hint, hint. So here, we're going to let u equal, we're going to let it be the numerator and denominator. But again, remember, we have a little more complex part being our u, so we're going to let that u be the denominator of 1 plus the square root of x. Taking the derivative, we know that the square root of x is x to the 1/2. So I take the derivative of 1 is 0, derivative of x to the 1/2 is 1/2 x to the negative 1/2 dx. So du is going to be 1 over 2x to the 1/2 dx. And some of you may be saying to yourself, hey, we have a square root of x in there, and that's the x. But this is a numerator. This, unfortunately, is in our denominator. So we're going to have to multiply this 2x to the 1/2 all the way in to the du. So we get 2x to the 1/2 du equals dx. So now if I come back to my integration, I'm actually bringing an x in to my integrand instead of getting rid of some x's. That's actually going to be kind of ugly and kind of nasty here for just a little bit, but notice our denominator becomes a single variable. That's just a positive u there, which is going to be helpful in the end. Not so much right now. So we've got x to the 1/2 here, and we have a square root of x here. Well, if we look up here, we have x to the 1/2 square root of x there. So u minus 1 equals that square root of x. So now I have the integration of 2 times x to the 1/2 is u minus 1 times 1 minus a u minus 1 over u du. We can go ahead and clean up this numerator. So we have 2 times u minus 1. We have 1, we distribute the negative here. This gives us a negative u plus 2. Again, over u du. We're going to now distribute this numerator out. This 2 is being multiplied to all it, so we could bring this 2 to the outside of our integration symbol. Multiplying this out, we get a negative u squared. We get positive 2u's plus 1u gives us 3u's minus 2 all over u du. Leaving that 2 on the outside of the integration. We now break this up. We get a negative u plus 3 minus 2 over u du. Now we can go ahead and integrate. Integration of negative u is negative u squared over 2. Integration of 3 is 3u's. Minus the integration of 2 over u is 2. Natural logs of the absolute value of u plus c. Again, if we multiply it 2 to the c, 2 times c is a constant, so it just gives us another constant. Now we can go and replace our u's with 1 plus the square root of x. So we have 2 times the negative of 1 plus the square root of x squared over 2 plus 3 times 1 plus the square root of x minus 2 natural logs of the absolute value of 1 plus the square root of x plus c. I'm going to multiply my 2 through if you want. The 2's here are going to cancel, which is nice for us. So we have the negative of the quantity 1 plus the square root of x squared plus 6 times the quantity 1 plus the square root of x minus 4 natural logs of the absolute value of 1 plus the square root of x plus c. You may be thinking, hey, I'm done. But wait, we're not. We can clean this up. We can square out this. If I square this out, I get the negative. 1 squared gives us a 1 minus 2 square roots of x minus square root of x squared gives us x plus 6 plus 6 square roots of x minus 4 natural logs of the absolute value of 1 plus the square root of x plus c. Again, we can clean this up a little bit. Negative 1 plus 6 gives us 5. 5, remember, is a constant. A constant plus c is still going to be c. So I'm going to add these three terms together, and that's going to be my c at the end. Negative 2 radical x plus 6 radical x gives me 4 radical x minus, here I can take up, or I can leave my 4 natural logs of the absolute value of 1 plus the square root of x. And that, my friends, is a nice, clean f of x function. Happy, happy, happy integration today.